Oh man, photoelectric effect is hard. I don't get any of this. All these dogs moving around and these old cats eating electrons. I wish someone was here to help me.
I can help you with that.
Where'd you come from, stranger?
Quantum tunneling, but you know, that's for someone else's video. Anyway, let me see what you're doing. What do we have here?
Got some photoelectric effect going on here.
That's a reindeer.
Yeah.
And these look like molecules, like biological molecules. That's ATP.
Yeah.
This is a biochem book.
Yeah, I know.
Yeah, I think that's the wrong book. You need one of these. Physical chemistry.
Nice.
Yeah, I jumped a little bit too far there. You might want to go back a bit. Right about here. But before I can explain to you the photoelectric effect, we should talk about the history first.
Cool beans.
Okay, Timmy. Normally when you ask people who discovered the photoelectric effect, the first person they would normally say is Albert Einstein. I mean, that's the reason why he was awarded the Nobel Prize in 1924, right? Well, that's where you're wrong. What Albert Einstein was recognized for was his discovery of the law of the photoelectric effect, which is slightly different. However, I'll get back to that later. First, let's talk about the man who actually did discover the photoelectric effect, Heinrich Hertz. One day in 1887, Heinrich Hertz was just chillaxing in his lab like a scientist when he discovered something rather peculiar. He found that when a metal was irradiated with ultraviolet light, it was able to generate electric sparks more easily than normal metal. Intrigued by these results, he quickly ran to publish them, not knowing the importance of his discovery. Let's fast forward a couple of years to 1901, which is when Max Planck finally solved the mystery of blackbody radiation. Now you may be asking, why is he important, and why do we even care? It's because this seemingly unrelated discovery helped lead to the final explanation of the photoelectric effect. His results led to two important discoveries. First was that the energy of the electrons were quantized, and second was the defining of an arbitrary constant, h, now known as Planck's constant. Going back to the discovery of the photoelectric effect by Heinrich Hertz, scientists began to explore the cause by applying classical physics. They predicted that as light intensity increased, so would the vibrations of the electrons on a metal surface, therefore allowing them to break away with the kinetic energy that was dependent on the light intensity and not on the light frequency. Surprisingly, when they tested this hypothesis, it turns out that the opposite actually occurred, where no matter how high the intensity was increased, the kinetic energy of the ejected electrons remained constant. In addition, it also appeared that there was a minimum frequency that must be applied to remove an electron called the threshold frequency, where below this threshold electrons are ejected. These experimental observations completely contradicted classical physicists and revealed that there was something at the quantum scale that was occurring that they did not understand. Finally, emerging amongst the confusion of classical physicists arrived Albert Einstein, who was the first to solve and piece the puzzle together by using Planck's constant. Planck, however, believed that light behaved as a classical wave, while Einstein, on the other hand, made his own hypothesis by claiming that radiation existed as small quantized packets of energy, now known as photons. Because of his contribution and explanation of the law of the photoelectric effect, Einstein won the Nobel Prize in 1921. Also due to his discovery of quantized packets of light, he helped formulate the idea of the dual properties of light and other particles such as electrons, which is an important cornerstone of quantum mechanics.
Oh yeah, man. That's some cool history. But how do you apply it?
Well, I'm glad you asked. I invited my friend the Quantosaurus Rex to help explain.
So what is the photoelectric effect? The photoelectric effect is when light hits the surface of a metal and electrons eject. Now, in this, we have these equations for the photoelectric effect. We have the work function, because you need a certain frequency of light in order to eject the electrons. If your frequency isn't high enough, the electrons won't eject. And then we have the kinetic energy of the ejected electron. And then we have Planck's constant, the frequency of the light used to eject, which will determine the energy, the velocity of the ejected electron, and the mass of the electron. Now, we have the kinetic energy of the ejected electron is equal to the energy from the light put into the system minus the work function. And from knowing the kinetic energy, we can determine the velocity of the ejected electron. But if we want to take an experiment, we need to work backwards. We could know the amount of energy we put into a system from the frequency of light. And we know the speed of the ejected electron from measuring it from a detector. But when we know this, we can solve for the kinetic energy of the electron, and then we can use this equation in order to figure out the work function of a material that we're working with. Okay guys, now I'm here to talk to you about the Millikan experiment and the photoelectric effect. So classical physics believed that it was the intensity of the light that determined the energy of it. So that the more intense the light, the higher the energy. When Millikan did this experiment, that's not what the results showed. In order to prove this, Millikan had a setup. It was a light shining against a metal plate, and then if the metal plate ejected an electron, it would travel through the circuit, hit the galvanometer, trigger that, so basically it showed that an electron passed. That's just a signal to show that an electron went through the circuit, and then be collected at the collector. Now, when Millikan used light of a low frequency, like red light, no electrons ejected no matter what the intensity of the light was. But when he used green or blue light, this was enough so that the electrons ejected off of the metal plate, went through the circuit, and then hit the collector. So this is pretty good evidence for the photoelectric effect. We can see that it's not the intensity of the light that determines if it will eject an electron, but the frequency. So pretty good evidence that the frequency determines the energy of the light. But this is not definitive. In order to put the nail in the coffin, Millikan put a voltage stopper in his experiment. What this voltage stopper did is it applied a force sending the electron back. So if I eject an electron off the metal plate with barely enough force to have it come off, it'll hit the voltage stopper and then get flown back. And then you won't see any sign from the galvanometer. But if I increase the intensity, nothing happens. You still don't see anything in the galvanometer. However, increasing the frequency of the light, so if I change my light from green light to blue light, we see the galvanometer go off. So the electron that got ejected had enough kinetic energy in order to bypass the voltage stopper and hit the collector. So when he saw these graphs, he determined that the intensity of the light determined how many electrons ejected off of the metal surface, but that the energy of the photons were determined by the frequency of light and not the intensity. This proved the quantum theory for the photoelectric effect and showed that the classical theory that they had up until now was false.